On March 2, 2026, targeted drone and missile strikes hit Qatar's Ras Laffan industrial city. The damage instantly severed one of the most critical material arteries of the global high-technology economy. Ras Laffan is the world's largest liquefied natural gas export hub. It functions as the planet's primary extraction point for associated helium, which is captured as a trace byproduct of the North Field's gas stream. Following the strikes, Qatar Energy's declaration of force majeure removed 5.2 million cubic meters of helium per month from the market. This represents a 33% contraction of the entire global supply, erased in a single afternoon. The immediate downstream casualty is the global semiconductor and artificial intelligence hardware manufacturing base. These multi-billion-dollar foundries require a steady, high-pressure flow of ultra-high-purity helium to operate their most advanced cleanrooms. While the digital economy appears to be built on intangible software, it remains physically tethered to the periodic table. A regional conflict in the Persian Gulf now directly dictates the world's capacity to produce compute power. The financial market reaction was violent. In March 2026 alone, over $200 billion in market capitalization evaporated from the semiconductor sector as investors priced in the risk of prolonged production halts in South Korea and Taiwan. By mid-2026, memory prices surged 130%. Helium-sealed enterprise hard drives, relying on the gas to reduce aerodynamic drag, rose 50%. These costs cascaded downstream, completely erasing the thin margins of the entry-level PC market, making the sub-$500 laptop impossible to manufacture. The contagion extends to the healthcare sector, where liquid helium is required to cool MRI magnets to 4 degrees Kelvin. Scarcity has delayed new installations and increased the risk of quenching, a catastrophic failure where the cooling fails and the helium is rapidly vented. National security is also impacted. Aerospace firms and NASA have been forced to delay launch schedules as military applications for purging and pressurizing rocket fuel tanks take priority over research and development. The helium shock acts as a universal tax on high technology. It demonstrates that supply chain assumptions built on the availability of cheap, abundant materials are no longer valid. To understand why a gas shortage stalls a modern economy, we must look at the microscale thermodynamics of a semiconductor fabrication plant. As chip architectures shrink toward 2-nanometer nodes, the heat density generated during the manufacturing process scales exponentially. Managing this heat is the central engineering bottleneck of modern logic production. This is most critical in extreme ultraviolet lithography. These light sources are notoriously inefficient, converting most of their energy into heat that can warp photomasks and ruin entire batches of wafers. Let's compare 3 gases for heat management. Nitrogen is inert, but its thermal conductivity is too low, causing wafer distortion. Hydrogen is conductive, but highly flammable and chemically reactive, destroying sensitive structures. Helium is the unique solution, absolutely inert with high thermal conductivity. Fabs use this for backside wafer cooling. Helium is injected directly behind the wafer to create a thermal bridge between the silicon and the cooled electrostatic chuck, allowing the machine to run at full power without melting the chip. Without the specific atomic properties of helium, the production of modern DRAM, NAND, and advanced logic chips becomes physically impossible. If helium is this critical, the obvious solution is to stockpile it. Yet manufacturers like Samsung and SK Hynix only maintain a fragile 6-month inventory. The barrier is the boiling point. At negative 269 degrees Celsius, helium is only a liquid within 4 degrees of absolute zero. Keeping it in this state requires immense energy and specialized infrastructure. This 40-foot cryogenic ISO container transports liquid helium. It uses high vacuum insulation and a liquid nitrogen shield. Still, heat slowly permeates. The helium boils, increasing internal pressure. At the 45-day limit, reaching 5.7 bar, a safety valve must open, venting and losing the gas. In 2026, the closure of the Strait of Hormuz forced shipments from Qatar to take routes lasting well over 60 days. In the helium trade, a maritime delay is a physical expiration. Crossing the 45-day threshold forces an emergency pressure release, resulting in the mandatory venting and absolute loss of the cargo. This logistical fragility is compounded by the fact that helium cannot be manufactured. It must be extracted from the Earth's crust, where it accumulates over millions of years. Helium is a byproduct of natural gas processing. In Qatar, it's just 0.04% of the gas stream, entirely hostage to this massive LNG infrastructure. This dependency creates a fatal structural flaw. If energy demand drops, or if a gas plant is attacked, helium extraction stops immediately. The technology sector's most important gas is at the mercy of the fossil fuel cycle. This chart shows the market's lack of redundancy. Qatar and the US together control roughly 75% of global supply. However, the 2024 privatization and depletion of the US Federal Helium Reserve removed the world's only large-scale safety buffer. Projects like Russia's Amur plant are inaccessible to Western tech hubs due to geopolitical sanctions, leaving the market nowhere to turn when Qatar goes offline. The global technology sector has built its most advanced infrastructure on a precarious byproduct of a few concentrated, geopolitically volatile nodes. The 2026 crisis marks the end of the open-loop era, where semiconductor foundries could afford to simply vent helium into the atmosphere after a single use. The first pillar of a resilient supply chain is decoupling from natural gas. This means investing in primary helium projects in stable regions like North America and Africa, where helium concentrations are high enough to justify extraction without LNG. The second pillar is on-site reclamation. Instead of a linear path from well to atmosphere, fabs must adopt closed-loop systems to recycle supply. Pressure swing adsorption uses adsorbent materials to filter exhaust, recapturing up to 95% of helium. Taiwan and Japan already achieve recovery rates over 70%. Regions that lag behind in this infrastructure remain existentially vulnerable to the next supply shock. This material security is the foundation of the artificial intelligence era. The data centers powering the next generation of compute cannot expand without a reliable supply of the chips and helium-sealed drives produced in these foundries. The resilience of the modern digital world is no longer just a question of code. It is a question of our ability to manage and recycle the most elusive elements on the periodic table.